first time it's been on today. Let me talk about a few, just a minor item or two. I'm not certain on this, but I believe I'm correct on it, that next Tuesday, I've got a meeting on the Birmingham campus, I believe at 10 o'clock in the morning, okay? So I'll probably have to cut my 8 o'clock class short if I even can make it 8 o'clock class. We'll just see. The meeting goes 10 till 11, and then I might have to be there for the first few minutes of the next meeting, but then I'll try to leave there by 11:30, so I'll be here by 12. So hopefully we'll start on time, but if not, don't go anywhere. I will be here, okay? That's next Tuesday. Thursday should be no problem, okay? What's that? Okay, say that one more time. Okay. It may have been that I thought my doctor's appointment was going to make me lose some, but it didn't. It was in the morning. And then I was worried about this other class, this other meeting, but I don't think it will either. It might make me a little late, but it won't make me miss, I don't think. Not going to move. Okay. All right, so except for that, but there were so many things I had planned to do this morning and didn't get them done, so I'm going to have to do them this afternoon, so we'll have to see. Okay. All right, any questions for anything we've covered so far in chapter 19? Okay. 19 again is building the Earth's surface, as opposed to the next chapter is going to be shaping the Earth's surface. Okay. Then after that, we got class this week and next week, and then when do finals start? 31st, which is a Monday or Tuesday or Wednesday, what day? Oh, it's a Monday, I think. I think 31st is the last day of class. I think we have class on Monday, and then finals start on the next day. Is that right? Not? That's what someone in my other class told me, so I took their word for it. I didn't go back and check the campus calendar. But anyway, we don't have many left, so how far we're going to get, I'm not sure, because we've missed, unfortunately, way too many classes. All right, we were talking about any questions on anything we've covered so far? All right, if not, we were talking about classifications of earth. Well, we're talking about earthquakes in general and different ways to classify them. Well, we talked about how to locate them. What is the actual location of the actual earthquake? What is that called? Focus. But most of the time people don't talk about the focus, they talk about the epicenter. And what is the epicenter relative to the focus? Yeah, location on the surface directly above the focus, that's it. Another way to classify earthquakes are the depth of the focus. Okay, and that's what we're going to talk about in this slide. And then we'll talk about how to measure earthquakes. Okay, so let's start with classification of earthquakes based on their depth. We have shallow focus earthquakes. The foci for these earthquakes are not very deep. Well, I say not very deep, down to about 70 kilometers deep, okay? That doesn't sound deep to me, does it to you? Like 42 miles deep? That's pretty deep, okay? But those are called the shallow focus earthquakes, down to 70 kilometers, which is about 42 miles. Okay, 85% of all earthquakes happen in those shallow focus quakes. Why? Because the surface rocks are more brittle. So if the plates are moving, the surface rocks will get hung up and then break. Okay, and that's what makes an earthquake. So the surface rocks are more brittle, more plate friction near the surface than you have deeper down, where it's warmer. Some of that plastomeric, materials that don't really hang up as much. The friction's not as bad. So most of the earthquakes, 85% of them, within the top 70 kilometers or 42 miles. Then we have the intermediate focus earthquakes, quite a bit deeper, from 70 kilometers, which is 42 miles, down to, and here I know they have a misprint, and I always forget which way they misprint it. Okay? That should be a 350, not a 300. Because you notice there's nothing in between 350 and 300. So let me get my pen set up for a dark color. So that should be 350 kilometers. So this will be from 42 miles deep down to, oh boy, about 200 kilometers. 200 miles. But those are intermediate, okay? That you're into the upper part of the mountain. This is mostly crust, okay? This is upper part of mountain. And then we have the deep focus earthquakes. From 350 kilometers, which would be, like I said, about, 200 miles, down to 420 miles deep. Whoa! Okay. I don't even want to drive that far on the surface. I can't imagine going that far down. Okay. That's in the lower part of the mantle. Why wouldn't any of these be in the core? The core is liquid. How can it have an earthquake? Everything slides past each other there. So these are way down in the lower part of the mantle. And this is only about 3% of all earthquakes would be that deep. So what does that leave for the intermediate? How many? About 12%, exactly. Why they didn't say that, I don't know here. That's 12% here, 3% there, 85% in the shallow focus, which is mostly the crust. Okay? Did you imagine the crust went 42 miles down? But it's a very thin crust, okay? Compared to the rest of it, it is pretty thin. But that's mostly the crust, okay? So that's how we classify shallow, intermediate, and deep focus quakes. Any questions on that? Next, we measure earthquake strength. Now, one way, and early on, this is how we measure. What were the effects of the earthquake? How much structural damage did it do to buildings? How many fires did it cause? What landslides did it create? How much displacement of land surfaces? Did it create a tsunami, okay, which is a tidal wave? That's one way to measure earthquake strength. How much damage did it do? Okay? Is that really the best way, perhaps? I'll give you an example. I can't remember the year right now, but it was something like, seems like January or February, there was an earthquake that hit pretty hard on Haiti. Y'all remember it? Okay. Devastating earthquake. The capital city wrecked, large portions of it. Just enormous amounts of damage. Okay? Within just a few months, there was another quake in Chile. Okay? A very powerful earthquake. Only did a fraction of the damage that the one did in Haiti. So which would you say? Haiti was the stronger earthquake? Actually, it was a much weaker earthquake. The difference is Haiti generally hadn't experienced many earthquakes, and their building codes were really slack, if existent at all. Most of the housing, most of all the buildings in Haiti were just sort of thrown together, okay? Concrete block, no reinforcing, no steel reinforcing, really nothing like that. So the enormous amounts of damage came more from the poor preparation than it did from the actual strength of the quake. Yes, the earthquake was strong, the one in Chile, but Chile It's on the ring of fire, okay, right? So it's used to having earthquakes. That's where plates are really colliding together. A much stronger earthquake, but because Chile's building code was really strong and rigorously enforced, and people were pretty much prepared, and I think they sort of lucked out. It didn't hit a high population area anyway, but it was a much stronger quake, but far less damage done in Chile. Did damage, and I mean it was major damage, but nothing like what they saw in Haiti. So just the effects of structural damage to buildings. If it was out in the middle of nowhere, it may have been a really, really strong quake, but it just didn't do a lot of damage to buildings because there weren't many buildings. So that's not the best way to measure it. Actually, I think, if not the strongest, one of the strongest quakes ever recorded was in Alaska. But I think it was pretty much a low population density area. And so even though it did a lot of shaking and stuff with a really major earthquake, it didn't create many lives, didn't do that much damage to buildings. Actually, it did do a fair amount of damage because it was near the ocean, and it may be that the focus was actually under the ocean. I don't know. It was a long time ago. I wasn't really studying it or thinking much about it then. But the tsunami, the tidal wave that came after that quake was strong enough that made it all the way to Hawaii and did significant damage there. So Hawaii almost had as much damage to the quake as Alaska did, even though it was located in Alaska. So it still wasn't. It was a major thing to send that big a tidal wave from that much distance. It was major. Okay? That was almost similar to what happened to one in the Indian Ocean. That was right shortly after Christmas, I think, a day or two after Christmas. The day after Christmas. Okay. And 26th of December. You remember the year? 04? That sounds about right. That one did a lot of damage where it did, for sure. But the tsunami went across the Indian Ocean and killed a lot of people in India, too, because lots of people live right near the ocean. It's a very convenient place to live, and it wiped out a lot of southeastern India, the populations on the beach, and even as far as Sri Lanka at the bottom. All of them received a lot of damage. So, yeah. So measuring the earthquake strength based on the damage to buildings, it's not the best way. Well, along came pretty sure he was Italian, the name Mercalli sounds pretty Italian to me. He came up with a scale based on relative intensity of the quakes. Okay? Now, he made a 12-point scale, intensity 1. They measured there was a quake, but no one felt it. Okay? Not very major, very, very minor. Up to 12, which is total destruction with visible ground waves. So again, kind of based on the amount of destruction, but it's supposed to be relative intensity. Okay? That was better, far better than just how much damage was done. So that was the Mercalli scale. All right, now they throw this in here, and I'm not even sure it's in the new text. Let me see. Before we move on, this is an example based on the other way we classified quakes, the one I forgot to mention before this. We talked about it last time. We timed the time difference between the waves, P waves and S waves. Okay? Now, here is the question. Which station is closer to the epicenter if one seismic station in Nevada receives P waves at 4:30:15 for 4:30 a.m. in the morning, 4:30:15, meaning 15 seconds after 4:30. S waves at 4:30:35, okay, while a different seismic station in California receives the P waves at 4:29:59 and the S waves at 4:30:15. All right? So which one do you think was closer to the epicenter? This is the example 19.3 on page 491. So which one do you think is closer to the epicenter? Y'all see it? A little louder? I can't hear, sorry. California. Why do you say California?
It says because the Nevada station in the city weighs 20 seconds apart, whereas the California station has, I guess that's receiving 16 seconds apart.
Right. That is exactly true and very good reasoning. But you know what else? The California station got it first anyway. So wouldn't that make sense? That would be closer to the epicenter. It was at 4:29:59, and the P waves and Nevada was 4:30:15. So yeah, it got it first. So it must have been closer. And then you're absolutely right. The difference was smaller too. So so you were thinking absolutely correctly, but you could almost tell by the time they first received it, they had to be closer too. So that just backs it up. Example 19.4, at what time does a seismic station receive S waves if P waves arrive at 11:51:51 a.m. and the S waves arrive 75 seconds later? So it has nothing to do with waves. It's can you add times together, which is not that hard to do, but it is interesting. Do you know how, I mean, you've seen me add times before, right? Okay. You want to do that one real quickly? Let me back off and do it right here. At what time does it receive the S waves if P waves arrive at 11:51 a.m. and the S waves arrive 75 seconds later? Now you could put the 75 there if you wanted to. How would you do it? Would you add 75 to 51? Or would you start with 75 and say, wait, what is 75 seconds? A minute and 15 seconds, okay? That's what I would do. I would write that 75 seconds as 1 minute and 15 seconds. Do you agree that's true? 1 minute and 15 seconds later, okay? Now you add 5 and 1, 5 and 1, it would be a 0. Why is that? Because 60 seconds makes another minute. Carry a minute, okay? And that would be 3, 5, 11:53:06. And sure enough, they got it right. What did that enhance your understanding of earthquakes? No, it's just adding time. I don't know. So it seems like sometimes they just throw in these examples just because we need some examples here, okay? All right. Maybe people did need that. I don't know. Before we turn the page, though, there's a science sketch. Draw a 4-panel cartoon illustrating the distinctions between the Mercalli scales intensity 1, 3, 6, and 9. We haven't gotten there yet. We'll get there. Okay? And then myths, mistakes, and misunderstandings. Do earthquakes swallow people? Sure they do. I've seen it in the movies. No, they don't. Okay? I've never heard of earthquake yet. You see it in the movies all the time. That's not what an earthquake is. An earthquake is the shaking. It's not ever really much opening at all. It's just shaking the mud out of things, but it's just a shake. It's not an opening. Okay? Sometimes you'll see visuals of that, like that plowed field that we had, the rows of crops, and you see they got offset. Yeah, you can see that, but there's no opening and plants falling in or tractors falling. Nah, that doesn't happen. That's in the movies. Okay, so I'll let you read it that. Then there's another closer look. Okay? Earthquake safety. And that's pretty much what we've got here, only I've got to erase this stuff. Okay. Here's pretty much your earthquake safety. I think this is pretty close to exactly what's in your text. Here it is. And you'll see it again. They love the slide, so they do it. Earthquake safety rules from the National Oceanic and Atmospheric Administration. During the shaking, don't panic. I think more deaths probably occur from panic than from the actual quake. Where was it recently? It was a soccer game or something somewhere, and there was something that happened, and scores of people got either killed or injured because of the panic. Not because of what happened, but because they panicked and started stomping on other people, and Looney Tunes trying to get out. Okay? So number one, don't panic. Yeah, it's scary, but keep control. Okay? If you're indoors, stay indoors. Okay? If you go out, something may fall on you. Okay? So if you're indoors, stay indoors. Seek protection under tables, desks, doorways. See, doorways have more support than, if you get under that, there's a lintel, they call it, across the doorway, holding the stuff above it. It's usually pretty safe, okay? So a doorway, surprisingly. Stay away from glass. That can shatter and things can fly inside, okay? Don't use matches, candles, or open flame. Douse what fire you may have. Why is that? A lot of buildings either cook with or heat with natural gas. So you have gas lines. If there's a good, solid shaking, some of those lines could be ruptured, broken, cracked. There could be small amounts of natural gas leakage. And if you have open flame, the big earthquake in San Francisco back around 1906, I think it was, not the Bay Bridge, but the earlier one. It seems like I read somewhere more damage was caused by fire than was caused by the earthquake. Part of that was a lot of the buildings were wood, okay? And the big reason was a lot of people were cooking with various types of gas, and things just started exploding like crazy. Houses caught on fire, and it was just a mess. So the fire actually caused more than the other. So if you have an open flame around, turn it off. And don't strike a match, even if you can't see. Were any of you here yesterday when the power went off? Okay, I was too. It got pretty dark in places, especially interior rooms, restrooms. Hallways weren't too bad because they do have emergency lighting. Those rooms like this one with windows, it was fine. I had no power to teach from, but fortunately we were doing a lab down in 259, and the students could see well enough to see the lab results. And we finished up, and they went on home. Then the power came back, and I taught my last class last night. So even though it's real tempting to light a match, guess what? Y'all all have cell phones, they have flashlights, right? Use that. Don't be lighting any matches, even if you feel somewhat spooky in the dark. Okay? Now, that's if you're indoors. If you're outside, probably a good idea to stay outside. But don't don't stay near a building. Okay? I hate to say this about them, but UAB, ever since we moved to Birmingham, seems like they're always building another building someplace on campus. And they throw them up there pretty fast, and they're tall, big buildings. And it seems like I can remember more than one, and I think more than 2 or 3 of those buildings. Now, not because of earthquakes, but something happened and the bricks start falling off. I don't know if they built them too fast or the contractors weren't careful. Because a lot of times the brick is not part of the structural unit of the building. It's just a facade. I bet you that brick out there is just for appearance. The structure is the concrete block, okay? And they periodically, when they're laying the concrete blocks, will stick a sort of a ribbon-like piece of metal, sheet metal type stuff, and they'll connect to the bricks, and that holds the facade in place. The bricks are not really any support at all. So don't come close to a building because the facade may come off. Stucco, bricks, other things. So don't say, oh, it'll be safe if we get near the building. No, that's not a good idea. Stay away from the building and definitely stay away from power lines. Okay? Stay pretty much out in the open. You're probably pretty safe there. Okay? And then don't run through or near buildings, because buildings are the danger. They could be weakened and by the quake, by the shaking. I'll tell this story. It wasn't an earthquake, but it happened. I wasn't home at the time. In fact, I was returning from my 3rd class midshipman cruise in between my freshman and sophomore years of college. My parents had planned to come up to meet me in Virginia, and I was going to ride home. They were going to give me a ride home. This is from Georgia. My older brother was leaving for his 1st class midshipman cruise. He was in Navy ROTC as well between his junior and senior years. And my parents had taken him someplace, Savannah or Charleston or someplace, to catch a flight to go to his the port where his ship was going to be leaving from. So they had gone. Now, my older brother and my younger brother had gotten into a little spat or something the week, a few days before. My younger brother didn't want to go. He wanted to spend the night with a friend in town. So my parents, rather than listen to them fuss all the way, they let him go spend the night. He did that a lot of times. No issue. So while my parents were out of town, I was out of the country. My older brother was heading somewhere else. My younger brother and his friends were riding around in Waynesboro, it's a pretty dead little town. They heard the volunteer fire truck making noise and going somewhere. He said, oh, there must be a fire somewhere. Let's go see what's happening. And to give them a little bit of credit, they actually tried to do something useful. It was a bunch of not too well constructed buildings real close to each other, and one of these, I think that was unoccupied. Some people must have been squatting in it or something, and must have been trying to cook some food because they had no electricity or other thing, and they caught the house on fire. And it was sort of a tinderbox building anyway, so it went up, and that's what was burning. But the other houses on the block were really close to that. So the house next door, they were afraid the fire was going to jump over, the wall was going to fall down on that and start setting that on fire. So they were helping the family next door move their furniture out, and into the yard. So they actually were trying to do something useful. The volunteer fire team had put out the first fire, and it looked like the danger of the next one catching was not very great. So I think they were going back and forth helping me move the furniture back in the house. And my brother was walking through between the 2 houses, and some really sharp member of the volunteer fire department decided, all that was left of that first house was the chimney. And he started, since he had the water there, spraying the chimney with water because we liked to see the steam come off of it because the bricks had gotten really, really hot. Well, the chimney had been weakened, probably wasn't a strong chimney anyway, and it knocked the chimney down. On top of my brother, who just happened to be walking between the houses at that time, and he was covered with bricks, very hot bricks on the sides of them, and he had some pretty major burns. So don't be walking near buildings, is what I'm saying. If there's been any disruption, and then a little bit of a perturbation could make that rupture, the thing that looked like it was fine, the chimney standing there, then suddenly it wasn't.
Is that a pretty good lawsuit?
He didn't do that back then, and he was a volunteer anyway. We knew who he was. He was not the brightest in school either. So, anyway. Now, if you're in a moving car, so if you're inside, stay inside. If you're outside, stay outside. We get in an open area. Don't go through and don't run through or near buildings. The chimney may fall on you. And number 4, if you're in a moving car, bring it to a stop as quickly as possible, but stay in it. Because the car can absorb a lot of the shaking that might be more damaging to you, and you've got some protection around it. The car springs will absorb some of that shaking. It will offer you protection. However, don't park the car under power lines. Because if they come down, you're not going to get electrocuted in your car, even though those hot wires may be on top of your car. It's when you step out of the car and provide them a way to ground, then you get electrocuted. So it's a good idea not to park under power lines, okay? They may come down on top of it. So that's during the shaking. After the shaking, check on your utilities. If you know where the natural gas switch or valve or whatever it is to your house or business or wherever you are, go over and turn it off if you know that. If you smell gas, open every window you can, no matter what the temperature is outside. Open those windows, shut off the main valve if you know where it is, leave the building. Natural gas explosions are deadly, really deadly. Report the leak to the utility. Don't re-enter the building until it has been checked out by professionals. Okay? If water mains have been damaged, if you know where those valves are, shut them off. Again, more damage occurs because of the peripheral stuff than the actual plate. Fires or water damage and that kind of stuff. Shut off the main valve. If electrical wiring is shorting, if you can get to the main switch and turn the power off to the whole house. Better that than start a fire from the electrical panels. Okay? Now, if the power hasn't been turned off, or if you have a portable radio, turn on the radio or television if you have power to do so, and listen for the emergency voice. Don't panic, and unless you're reporting something like gas in a building, fire in a building, flooding in a building, or something like that, stay off the telephone, okay? Because all of a sudden, all the lines are going to be jammed. And when they are jammed, emergency communications can't happen as easily. So stay off the telephone except to report some of those emergencies. Stay out of severely damaged buildings that could collapse, because quite often with earthquakes, you have aftershocks. Okay? Now picture this. That pressure's been building up for a long time, and finally it lets go. Well, now everything shifts, and something else may now get stuck somewhere further up or down the line, and then with a little bit of effort, it's going to let go too, okay? And that may be minutes later, hours later, okay? And occasionally, I have heard of aftershocks being almost as strong as the original quake. Most of the time they're not, but if a building is pretty badly damaged by the major part of the quake, just a little bit of additional shaking could bring things down that were otherwise looked like they were staying up there. So watch out. Stay out of damaged buildings because it could further deteriorate with an aftershock. Do not go sightseeing. Now, after some of the tornadoes that we've had in the area and in the state, one of the worst things that happened, number one, everybody gets on the phone to call and see how everybody is. Now, that's sort of normal, okay? If you have family, elderly, grandparents, something like that, or young kids in daycare or something, and you really are worried, yeah, you're going to get on the phone and try to find out. Try to minimize that as much as possible, because guess what? If you're not there, what are you going to do about it anyway? I mean, you can't really do much. But then the next, besides that, probably the next worst thing that happens, people, wow, did you see what happened in Brett City? Wow, let's go see. No, let's not go see. Yeah.
The eclipse that's coming across.
Yeah.
Oregon has already issued a state of emergency because they're going to have people coming to that area because it's going to be totally dark there.
Uh-huh.
They saying a state of emergency because they expect the phone system to go down. People being on the phone.
Yeah.
And traffic to be locked up.
Yeah.
A number of people being a great number of people
Right.
in town.
And emergency vehicles aren't going to be able to get through. Yeah. So they're very proactive. I didn't know they had done that already. That's more than a month away still, isn't it? Wow. And they're already doing a preemptive state of emergency. That's pretty interesting. Wow.
Telling people to stock up on at least about 3 days worth of food.
Oh, wow.
Stay in the house.
Wow. That's amazing. And that's a very positive thing. That's not anything natural disaster or anything. So please don't do that. You'll only hamper the efforts of emergency personnel and repair crews. And I actually heard of people, I believe it was Pratt City, that when the tornadoes went through there, they had trouble getting home because so many other people were trying to drive through at sea that the state police and the local police were shutting down roads. They said, look, but I live there. I need to get home. My kids are there or something like that. So they had to, but everybody was telling them that, because they wanted to go see what the damage was, So it really made a bad situation for everyone. All right. So those are important things, but let's get back to the Mercalli scale. I hope we'll get to Mercalli scale. Nope, it didn't show up, okay? It's in the text, though. No, it isn't. That's the Richter scale. Where's Mercalli? I guess this edition of the book doesn't have the Mercalli. Well, wait, here it is. It's in the text, basically. Well, they came out with a Mercalli scale, and then, and here's some of what I was just talking about. In January 2010, strong Haiti earthquake collapsed more than 300,000 buildings. 300,000 buildings, not people, buildings, okay? Then in February 2010, 1 month later, the stronger Chilean earthquake collapsed more than 500,000 buildings. Injuries and death usually result of falling debris from crumbling buildings or falling bridges. Fires from broken gas pipes was a problem in the 1906 and the 1989 earthquakes that you were mentioning in San Francisco and the 1994 earthquake in Los Angeles. Broken water mains made it difficult to fight the 1906 San Francisco fires, but in 1989 they used fireboats and fire hoses using water pumped directly from the San Francisco Bay. So yeah, pretty major. Now, effects of an earthquake on people and building, the relative intensity, the modified Mercalli scale expresses intensities, Roman numerals. So yeah, they give some of those there. And that's why the science sketch, it says draw 4 cartoon panels that would represent the difference between level 1, level 3, level 9, and level 11. No, 6 and 11. Okay, you can read that and see. Now we move on to what we currently use, the Richter scale. Who in the world do you reckon Charles Richter was? Name sounds sort of German, doesn't it? He was American, Caltech, I believe. Okay, he came up, and rather than some relative intensity and stuff like this, he based it on the actual seismographic recordings. He measured the swings, the closest ones to the quake, did that, set up a logarithmic scale. Now, do you know what that means? We're going to use base 10 now, okay? On a log scale, a 3 would be 10 to the third, 1,000. A 9 would be 10 to the ninth, which is 10 to the third is 1,000, 10 to the sixth is 1,000,000, and 10 to the ninth is 1,000,000,000. So what you got is something going from 1,000 to 1,000,000,000, okay, in a 3 to 9 range. So what a logarithmic scale does is take huge numbers and gets them down to a much more usable scale, which also has other implications. By the way, a Richter scale number 3 is not usually felt. Okay, 9 is the largest measured so far, and I'm pretty sure that was one in Alaska. So they have had, I think, maybe one other 9 somewhere since then. It seems like I remember hearing about it. Okay, now these are the Richter scale magnitudes. 0 to 2. These can be detected on these seismographs, but no one feels them. Okay? So 0 to 2 would be smallest detectable earthquake, but you really don't feel it. 2 to 3, they're detected and measured, but still generally not felt. But when you get to 3 to 4 range, they're felt as small earthquake, but generally no damage. Okay? You feel the shaking, usually no damage. I think that's what we had at the farmhouse in Georgia. Actually, the earthquake was a very minor earthquake somewhere in Virginia, and North Carolina, South Carolina, Georgia. A sign we had on the wall fell off. That's the only thing we noted. We thought, why is this on the ground? And we asked our sister-in-law who lives over there. She said, oh, that must have been the earthquake. The earthquake? I had heard that there had been an earthquake in Virginia, and it did some minor but significant damage to the Washington Monument. Y'all know what Washington Monument is. Big obelisk that's in almost the center of D.C. in the mall there. And it used to be that people climbed to the top and saw all of Washington from a real high vantage point. And it was a real popular tourist thing to do, because it's the tallest thing in D.C. Well, it did enough damage to it, they had to close and not let people in there until they got the damage assessed and then repaired. And I think that may have been done by now. Okay, so I'd heard about that.
Capitol building.
And the Capitol building had some damage too.
I think they still got the scaffolding around.
Really? It's not at all surprising. So, there's a big old building, and they have some damage that is probably not an easy thing to correct. Okay? Wow, I didn't know that. So, as far away from Georgia, it was felt, but no damage. Up in D.C., there was damage. 4 to 5, minor earthquake with local damage. Okay? 5 to 6, moderate earthquake with structural damage on buildings. That's probably what happened to the Capitol building. 6 to 7, strong earthquake with destruction. So when you get in this range, yeah, you can do that. And if I'm not mistaken, the Haiti quake was somewhere right in these. I think it's probably there. 7 to 8, major earthquake with extensive damage and destruction. That was the Chilean earthquake. I don't remember what one on Indonesia was. Okay, off Indonesia. It was, wow. Yeah, man. But 8 to 9 is a great earthquake, and generally right around it, total destruction. There's no amount of earthquake-proof building that you can do if you get hit by one of those. I mean, it's going to tear things up. It's the lower level that you're got some protection for. Okay, now, because it's a log scale, this is what I was going to say. Let's take a 4. That would be 10 to the 4th. A 6 then would be 10 to the 6th. Is that just a little stronger than a 4? Generally, two zeros, 100 times stronger than a 4. Okay? So when you're talking about a 3 to 9, that's not 6 times more powerful. That's 1,000,000 times more powerful. 10 to the 3rd to 10 to the 9 would be an order of 6 magnitude. 10 to the 6 is 1,000,000 times stronger than 3. Okay? You're talking big, big numbers here. Now I'm saying that sort of generally. Let me read you the actual thing. An increase of 1 on the Richter scale means the amount of movement of the ground is increased by a factor of 10. Movement of the ground. The amount of energy released is increased by a factor of 30. So the 1 is 1 power of 10. The energy is 3 times 1 power of 10. So that would be 30 times. Okay? So an earthquake measuring below 3 on the scale is usually not felt by people near the epicenter. The largest earthquake measured so far had a magnitude greater than 9. But there is actually no upper limit to the scale. The highest one we've measured has been greater than 9, but there's nothing to prevent them from being bigger. So, example 19.5 says, compare the energy released by an earthquake of a 7.2 magnitude quake to that of a 5.2 magnitude quake. The energy. What do you think that would be? .2 is major earthquake with extensive damage and destruction. 5.2 is moderate earthquake with structural damage. So what's the difference in energy? Every point on the Richter scale represents 30 times the energy now. So 1 point would be 30 times stronger, the next point another 30 times stronger, 30 times 30, you don't add them, 30 times 30, 900 times stronger. 900 times stronger. 2 points on the Richter scale. 900 times more energy was released by the first earthquake, 900 times more than the second. Let's look at 19.6. Compare the amount of movement of the ground, surface wave amplitude, associated with the 2 earthquakes from that. What would be your conclusion there? Each point there is worth a factor of 10 on the of movement. So 10 times 10, two digits on the Richter scale would be 10 times 10, 100 times more movement. Quite a bit. All right. And guess what? I said they liked it. They showed it again. The same thing we have here in very small print, they have here again. Okay, everything we did before. I thought it was here twice. I couldn't remember for sure. When we get to tornadoes, if we get that far, we are going to see the safety for tornadoes almost the same thing, except it says if you outside move away from building, it's still probably stay in the open. No, with a tornado, get in the ditch. Okay, get somewhere as protected as possible. Okay. But the rest of that is pretty much true. Okay? So everything we just said that's printed again, easy to read here. All right, that finishes 19.3. Earthquake, basically. Now we're moving to another result of plate tectonics. This is how mountains form. Okay? Origin of mountains. Now, what is a mountain? A mountain is an elevated part of the Earth's crust rising abruptly above the surrounding surfaces. Okay? Now, generally, there's a couple things in that definition that are sort of interesting when you consider. If I said, what's the tallest mountain in the world, what would you say? Say again? Mount Everest in Nepal, I believe, but somewhere right in there near a border, you know. So that's the tallest mountain in the world. But by this definition, not really. Okay, it is the tallest. It has the highest elevation. But Mount Kilimanjaro in Tanzania, Kenya, that area, is actually rises greater above the surrounding surface than Everest. Because all around Everest, you got other mountains, okay? So Everest is just the tallest among a bunch of tall ones. But Mount Kilimanjaro, sort of in a flat area, and all of a sudden it goes way up there, rising above its surrounding surface a greater distance than even Everest does. However, it's not as tall as Everest. Okay? Now, what is the origin of these? It says created by folding or faulting of the crust. In a broad general sense, yes. But we'll see here there's three basic origins. Folding, yes. Faulting, yes. But you have a third kind, volcanic activity. Which you might say, well, yeah, but indirectly that's coming from faulting of the crust too. That's why you have volcanic activity. So in a general sense, yes, but this is a separate class. So you have folded mountains, fault block mountains, and then you have volcanic mountains. And sometimes you have two or all three of these in close proximity to each other too. It's not like they're clearly one or the other. Sometimes they're kind of a mix between the two or three. Okay, I was going to say something else, but let's just move on. So let's first look at the folded and faulted mountains, and we'll start, I think, with the folds. And we've sort of been through this before, but we weren't just talking about mountains. We were just talking any kind of modification of a plate or a crust. Okay. You have what they call domed mountains. They begin as a big, broad, arching fold. What do we call that, by the way? Anticline, exactly. Okay? And now, really, though, I don't think it should be called a mountain. To me, this is what Stone Mountain is in Georgia. Okay? Just one big, broad chunk of granite that just sort of a dome mountain. As far as I can tell, that's what it seems like. Now, what happens with this, the underlying sedimentary rocks weather away, leaving more of the resistant granite peaks, and that's what Stone Mountain. The other stuff weathered away, but there was something there that created that granite in the first place. So we'll talk about that a little bit later in the chapter as well. Here is a picture that kind of shows what we're talking about. This would be like a dome, broad arching fold. That's how it begins. The things just start rising, okay? now. They don't just start. This may take tens of thousands of years. You never see it happening, but if you look one generation to 2 or 3 generations later, it's like, what, bigger than it used to be, and you'd probably be right. But it might take more than 2 or 3 generations to tell with it. Geological time is a long time, okay? But if it started this way, and you can well imagine the pressure is coming from underneath, okay, pushing this up. Well, the crust is a little brittle, you know, and you're stretching this crust. And you may have cracks and crevices that are caused by the stretching of this. And when that happens, then this topsoil is broken up and washed away, and other things do, and that keeps happening until what you find is the highly resistant to erosion granite, probably that's in the middle there. It started way down here, but here it came up. That is kind of the beginning of a dome mountain. This you might say was a dome mountain, but that's not super long lived. This will hang around for a while. And if it continues happening, it may actually grow them as well. Okay? So the overlying sedimentary rocks weather away, they get washed away, they get eroded away, leaving the more resistant granite peaks. This may be a little bit of granite in here, and then maybe soft material there, and then harder again in the middle. Hard to say. Whatever you got, that's what you have to live with. Now, I wish they had the picture they do in the book. And maybe that should have gone right there. No, right there. There's no picture there. Figure 1719 shows the folded structure of the Appalachian Mountains revealed by weathering and erosion. This is a photograph taken by the Skylab spacecraft, I guess you would call it. This, sorry, right around the Virginia, Tennessee, Kentucky boundary area. And just looking at that, you could almost easily imagine these foldings happening. Okay? Seems like the last several Monday and Wednesday nights, because I get off about 9:15, Dr. Bryant, who teaches next door, gets off a little bit later, and for the last several times, he had been getting rides. His car broke down. He's been getting rides with a niece, but I think she doesn't like to come back late at night and pick him up, so I've been giving him a ride home. And as I go down, actually as I come back, he's near Oak Mountain. That's one of these folds, because it's not just a mountain, it's a line of mountain. And we come off of that, go through a pretty, not a super deep valley, but and then here we go again, and we go up Shades Mountain, which is another fold, I think. And then, right near, Lakeshore and Oxmoor and stuff, you basically hit Red Mountain, okay? Another climb, okay? It's not very tall, but that's just a ridge. And you can see this mountain is really a long string of a ridge there, okay? The clouds that you see there, almost bluish in color, are over the Blue Ridge Mountain, okay? How appropriately named. Okay. So those are folded or faulted mountains. Now we go to the faulted side, okay? And we're going to look at fault block mountains. What the fault block mountains are, the folded mountains just sort of come as these folds, general mounds that come up, you know, and happen. The fault block mountains generally rise sharply along steeply inclined fault plains, like this, okay? I don't know if you remember when we talked about this wall would be called a what? Hanging wall. No, that's foot. That's hanging. Not hanging. The one on top is always hanging. The one on the bottom is the foot. Yes. That's foot, then hanging. Okay? Now, remember the book also introduced it and called these things ravens and horse. These were the ravens and those were the horse. Okay? Never use those words except for this. Okay? That was the original fault blocks. Okay? That happened. Then, over time, and this is what a lot of next chapter is going to talk about, the edges start getting wearing off, where there's been a break, things have been loosened or fractured a little bit anyway, and now wind and water and stuff start wearing those out, washing the sediments down into the valleys, the gravens, and these get rounded off, so then you have mountains that look like this. Now, you might say, that's sort of what those look like too. And it does a little bit, except it just looks like this with more regular folds than they would be faults. Okay? And the faults rise up pretty steeply. Even after they've worn away and some of the sediment has filled in the valleys and the mountains and worn them off, they still are pretty abrupt next to them. I know that when I was driving out west on my first duty station in the Navy, my word, I saw the Rockies or the Sierra Nevadas or whatever they were show up a long way down the road, and it seemed like I drove another day or two, and they just grew ever so slightly because you could see them, that flat plain, you could see them pretty cloudless, you could see them rising there. At first they were sort of a bluish haze, and you didn't know what they were. Then they got closer, you saw a little bit of white on the tops and stuff. You knew those were mountains. And they kept growing day by day by day, but very, very slowly. Soon, it was very abrupt. Okay? So those are fault block mountains. And then the third kind are volcanic mountains. What is a volcano? Volcano is a hill. Usually you think of it as a mountain, but it may only be a hill or a mountain formed by the extrusions of lava. What in the world is lava? Magma that made its way to the surface. It's magma when it's down there, lava when it gets to the surface. Or rock fragments from the magma below. Okay? So what could be in that extrusions that come out are fragments of rock that were picked up along the way, and they come out with the lava. Now, they mention the structure here, but never illustrate it very well. Sorry about that. Okay? That is a picture, I'm pretty sure, of Mount St. Helens. Yeah, here it is. The top of Mount St. Helens several years after the 1980 explosive eruption. Excuse me. Now, notice it's still spewing forth some steam. It ain't over till it's over. There's no telling it may blow its top again. Do you think that mountain grew during that eruption? Why not? Yeah, it knocked some of the highest peaks down. I think the side over here that you don't see had been the taller part. And when the eruption occurred, that part of the mountain actually fell off. It went tumbling down the sides, and lava went after it and stuff like this. So in some areas grew a little bit, but overall it actually shrunk because it blew off on it. It blew its top. It got mad. You can basically almost imagine these were the lava flows. Certainly no trees left growing there or anything else. A lot of fresh material brought to the surface. Okay. So we still haven't seen anything that suggests itself for these structural elements, the vent, the crater, and the lava flow. I'll tell you right now, that's the crater right there. It's so covered in steam, it's hard to tell, but that's the crater. These, my assumption, are the lava flows, okay? Where that went down the side of the hill. The vent is kind of hard to say. That's why I can see if the book addresses that, or the slide set addresses it any better. I don't recall that it does. No, it doesn't. Okay. It's almost 120, which, no, it's not right. Should go to 150. I'm having a little bit of problem breathing, so would y'all mind taking a very quick break now? I noticed that Brian did go out, and I sort of hate to keep talking with a third of the class missing. Actually happened. I had eaten lunch fairly quickly because I had all those interruptions. I hadn't drunk anything, so I was somewhat dehydrated. And then this morning at the doctor's office wasn't very much opportunity to. So I think this, my sister was saying, we need some fluid. So I had some tea left over from lunch, so I drank some of that. Hopefully I'll feel better a bit. All right. We were talking about types of, well, had we gotten to types of volcanoes yet? Yeah. Well, I said the structure of the vent, crater, and lava flow. Yeah, we could see the lava flow, the crater. The vent was not particularly easy to see. Let's go back to that picture. I would be speculating to try to guess here. This could be just clouds of the steam. That's mostly steam coming out now, and they could be moving down the mountain. But it could be, that could be up in the air somewhere, or it could be there's a little vent somewhere on the side that is also letting out steam. And I think that's what they mean by vents. The crater and lava flow is kind of obvious there. The vent would be any other place that there may be a release of pressure. Okay? So let's look at the types of volcanoes, and as we look at these, maybe we'll see some of those others as well. Okay? And this begins with the shield volcanoes, which are, trying to find where that, it's on page 495, the right-hand column, basically the first paragraph. Okay? 3 major types of volcanoes: the shield volcanoes, cinder cone, and composite. We'll start with the shield volcano. Constructed of solidified lava flows. Okay? Mostly lava. That's most of what makes up a shield volcano. Now, generally in a shield volcano, this doesn't quite sound scientific, but it's sort of what the lava just sort of oozes out, okay? And it just sort of spreads. So these are broad, gently sloping cones, if you could even call them cones.
So it's just solidified lava.
Yeah, oh yeah, yeah. That's most of what it is. The lava flow is solidified lava. Exactly. Okay? So you have these broad, gently sloping cones. I would almost call them mounds looking. Okay? And let's see if they have a picture. They have several good ones in the book. This is Mauna Loa. Yeah. Well, this is exactly your figure 921 in the text. The upper part says a schematic cross-section of an idealized shield volcano. And then the picture is of Mauna Loa in Hawaii. Okay? Now, this kind of indicates what I was talking about in a small way. Number one, there is and I don't want to say this is the vent. I think the vents are the things over here. But you have some sort of crease or crevice or something that allows the lava to reach the surface, okay? And usually, if there is, near the top, that's usually called the crater. Now, this doesn't have much of a crater, okay? And the shield volcanoes typically won't, okay? But they may have other places where some of that also comes up. Now, this has been happening for a long time here, and all under the water, you had these basalt layers where the magma made its way to the surface, became lava, and spread out over the surface. It just kept spreading as it came out slowly and gradually and built these broad, gently sloping, barely able to call cones, and that's your shield volcano. Look at that, just very broad, gently sloping, okay? Now, and again, I'm not real clear of whether they call these vents or just other craters. That looks like it's the major crater there. Not much of one, but is. And this, I don't know if Mauna Loa is still active or not, but it has been active quite a bit in the past. And this is basalt. And they say, call these the layers of basalt that have been formed here. When the eruptions do occur, they're not usually the big explosive, they just happen. And it just oozes and adds to what's already there. Okay? There's Mauna Loa. I don't know if y'all are aware of this. I guess someone in the Navy had a weird sense of humor. I was on an ammunition ship in the Navy, my first 3 years on active duty. And I discovered that they named ammunition ships after active volcanoes. Okay? Didn't make you feel too good, but if you did have a fire on board, you're going to make one big hole in the water, because, but we never did, not going to. I mean, it's, they're some of the safest ships in the Navy because they took fire safety very, very seriously, and they kept up with all sorts of things. We were the USS Kilauea. The Kilauea is probably the most active volcano on the planet. It just is always spewing lava and has been for years, maybe decades. It's not erupting, blowing things, it's just spewing lava, just about all the time. Mauna Loa, this one, looks like it did this in the past, and then stopped for a while, then did more and did more and did more. It looks like it's not very active now at all. I don't see anything happening. There was a Mauna Loa. There was a Mauna Kea. There was a Vesuvius. It was out of commission. Shasta, Mount Katmai. My barber used to be on Mount Katmai. It's out of commission too. Mount Hood. And I'm probably missing several, mostly. Now, in the old days, they even had some other names like the nitro and like nitroglycerin, and there's another one like that. I can't think what that one was, but it was sort of like that. Very explosive type names, okay? Those are out of commission too, the nitro and it's not petrol, it's something else like that. Okay, so those are your shield volcanoes. Here are your cinder cone. Well, no, actually this isn't a cinder cone. They do not have a picture of the cinder cone. The cinder cone volcano is constructed of rock fragments, not just solidified lava flows, but rock fragments. That's what they call the cinders. I think of cinders as being little pieces of soot and ash. These are big old rock fragments. And that's pretty much, when you mentioned Mount St. Helens blew its top and had a lot of rock fragments that went down into the thing. So the cinder cones are constructed of the rock fragments or the cinders. They're generally steeper but smaller, meaning not as big around as the shield volcanoes. And that's the one we don't have a picture of either in the on the slide set, nor on the, no, there is one. The old edition didn't have one, the new does. On page 496, Sunset Crater, a cinder cone volcano near Flagstaff, Arizona. Okay? It's a real pretty little volcano there. Okay? So that's your cinder cone. They, again, constructed of rock fragments, or the cinders, that broken pieces of the continental crust generally. Okay? They're smaller but much steeper, whereas the shield volcano is great, big, rounded domes. And these are much steeper but smaller. And then we have the third kind, which is the beautiful kind everybody always thinks of, and that's the composite volcanoes. Alternating layers of cinders, ash, and lava flows with volcanic mud. So it has it all. It has the cinders, it has the lava flows, it has ash, it has volcanic mud, it has all sorts of things on it. And this is a representation of that. Now again, I'm not real clear on what they're saying. To me, this is what I would call a vent. I don't know if that's what the book calls a vent. The main crater is up here. The vent is another source of this, but it's a lot less major than this. And then you have rock fragments down here giving it the cone type shape as opposed to the round type shape like the cinder cone have. But it also has lava flows, volcanic mud, ash, all sorts of things there. These are really hard to read. Something lava flows. Boy, I can't read that. Oh, older lava flows, older ash deposits. These are the ones down here. These are the lava flows. These are ash deposits here. The newer ones, of course, they're the top. This is a cutaway view. Some of these are embedded in there. Okay, the newer ones are on the top, on the surfaces. The crater is right in the center. The more recent flows and deposits are closer to the top. Okay, these make the big, beautiful volcanic mountains. I think both this one that you see here is a top view. A side view, and the one in the book is a top view of Mount Shasta, a composite volcano in California. It says you can still see the shapes of the former lava flows from Mount Shasta. Now, the top view shows them better, but I mean, right here you see some of them, and that's a long way off. This is down the mountain, but you see them here. It looks like there had been a secondary crater here with a major crater there and the lava flows here. But then in between you had the ash deposits and other things as well. So it's volcanic mud, whatever is in there. But there's a big, beautiful Mount Rainier, Mount Shasta, Mount Hood. Those are all these. Now, none of the ones I mentioned except Mount St. Helens, they're all been extinct for quite a while. Does that mean extinct mean they're never coming back? Not at all. Everybody probably thought that of Mount St. Helens. It came back, she came back with a pretty big vengeance, okay? And she could blow again, Shasta could blow again. I don't know for certain what Crater Lake is, whether that's a cinder cone or a composite, but that is the crater is completely filled with water. It's filled a lot with water, and it is one, I've never been there, but from what I understand, one beautiful, beautiful lake. Okay? If it ever goes, there's a huge, beautiful recreation area not going to be there anymore. Something else will be there, but it won't be that.
So what kind of volcano is Yellowstone?
Okay, I think it was probably a composite. I'm not absolutely certain. It was one major one, because that Yellowstone Lake is huge. You don't even picture that as being in a crater. It would only, you almost have to get up in a plane and look down on it to see, oh, that was a crater, or at least part of a crater. I mean, it is so huge. And it has water coming in and water going out, so you don't think of it. You think of it as just a lake, but no, that's actually a crater lake. And evidently, when that one blew, it was major. So that was long before we were ever here. I don't know if the Native Americans have a history that goes back and explains that, or if the tribes that were here when we got here didn't know anything about it either. The tribes that were there before them, I don't know. That was one major. And this is where I get the concept of the vents. All that stuff happening in Yellowstone National Park, which is a huge park. I was just talking with my doctor today. We talked more about dogs and vacations than we did about disease, but we talked about the disease too. Nothing much happening, so there wasn't a lot to talk about. But I told him that my wife was going, the break that we have between summer and fall, Karen's got meetings in Park City, Utah, so I'm going with her, and we're going to drive over to Wyoming and visit the Tetons and Yellowstone again. It's just such a beautiful area. Nice time of year to get away from this heat and humidity up to where it's a little bit cooler and nicer. And he said, yeah, I was thinking of taking my family, but it's such a huge place, you just can't see it in a day. I said, no, you can't. You need to plan several days to see it all, because there's just features all over that park. But such a collection you'll never see anywhere else on the planet. I think Russia or somewhere in the former Soviet Union, there was a feature that may have included 3 or 4. This includes just about every feature you can imagine. And you'll see smelly stuff coming out here and vents there and hot water here and stuff. And I mean, to me, those are vents. You know, I don't know if that's what the book is calling the vents. They never illustrate what the vents are. Let me see if this new edition even mentions any more than just naming the vents. The last edition didn't. I don't see it here. Meanwhile, now that I'm looking, they named several. Mount Garibaldi, which I'm pretty sure is in Canada, just over the Washington border. Mount Rainier, which is in Washington State. Mount Hood, which is Washington, Oregon area there. Mount Baker, which is somewhere right in there too, probably Oregon. About 10 other volcano cones of the Cascade Range in Washington and Oregon could erupt next year, in the next decade, or in the next century, okay? History and plate movement make it very likely that any one of those volcanic cones in the Cascade Range will indeed erupt again. And the last one that did was Mount St. Helens, after having been dormant for probably hundreds of years, okay? So.
I saw a news article, I think last week, where he said that Yellowstone,
Yeah.
the geysers had started shooting lava at it for the first time that they could remember.
Oh, really?
Yeah.
I hadn't heard that. Old Faithful, or just some of the geysers? One of the other ones, right?
So he got lava at it.
That is getting to be a little scary.
Yeah.
You have a feeling that vent is venting more than steam now. Okay. So it could be things are happening.
Same article said that if that were to erupt, it would take the whole nation with it.
Oh, it definitely would. Now, there's not that many people who live there, but I mean, there's thousands who visit there probably every month that it's open. I mean, in the wintertime, still people go there, but mostly it's snow. It's sort of like sleds, but they're powered. It's like a ski-doo, but on snow. I can't think what they call those, but they tried to sort of restrict them a little bit, but it's just total beauty anywhere. But there's still places along the Yellowstone River there, the water will still be 72 degrees, even though it's icy and snowy everywhere else, because it's right above all those areas that bubbling up warm mineral-like waters. And the animals know it. Okay. All right. Other features. Before we get to these, this is one of the last slides here. Volcanoes do and have and will continue, like you just said, to change the world. Okay? Now that sounds like an overstatement, doesn't it? A volcano is just one little part of the globe, right? They mention several here. The most discussed change came back in the 1815 to 1816 after the eruption of Tamburo in Indonesia. Okay? Probably part of the same fault that caused the earthquake, more recently. The Tamburo eruption was massive, blasting huge amounts of volcanic dust, ash, and gas high into the atmosphere. Most of the ash and dust fell back to Earth around the volcano, but some dust particles and sulfur dioxide gas were pushed high into the stratosphere. Known today that sulfur dioxide from explosive volcanoes reacts with water in the atmosphere, forming tiny droplets of sulfuric acid, a very strong corrosive acid. That's in your batteries in your car. Really strong, okay? Have you ever splashed any of that on the shirt? It's now a perforated shirt, isn't it? Yeah, holes all over it, just eats right through it. On your skin, it feels like it's perforating your skin too, burning like crazy. So in the stratosphere, there's no convection, so the drops of acid and dust from the volcano eventually form a layer around the entire globe. The haze remains in the stratosphere for years, reflecting and scattering sunlight. The effects of the Tamburo blast around the world, fantastic brightly colored sunsets from the added haze in the stratosphere. On the other hand, it was cooler than normal, presumably because of the reflected sunlight that did not come back down to Earth. The whole planet was affected by that one really massive volcano eruption. It snowed in New England in June 1816. June, first month of summer, it snowed in New England. It was that cold, and you account for it by 1815, eruption of Tamburo. Crops failed, and 1816 became known as the year without summer for much of the world. Okay, amazing. Okay.
Affect both hemispheres?
Yeah, you have all these layers in the atmosphere, and one of the uppermost is the stratosphere, and it got all the way up there, and that took it around the globe. Okay. Another one was 1982 eruption of El Cajon in Mexico created enough haze in the stratosphere to reflect 5% of the solar radiation away from Earth, and researchers estimated that El Cajon eruption cooled the global temperatures by a few tenths of a degree for 2 or 3 years. That probably offset global warming a fair amount. If we hadn't had that, we could have been hotter now. In June 1991, the Filipino volcano, Mount Pinatubo, and this was probably 5 or 6 years ago when I was teaching this class, there was a woman who was from the Philippines, and she lived near Mount Pinatubo, and she knew exactly what this was talking about because her family was affected by it, blasting twice as much gas and dust into the stratosphere as El Cajon about a decade earlier. The dust from Mount Pinatubo remained in the Earth's atmosphere for the next 10 years. The haze from such eruptions has potential to cool the climate by as much as 0.5 degree Celsius, about 1 degree Fahrenheit. So, you know, lots of things happen. These are not just minor isolated incidents. The big eruptions like that can really cause a lot of issues. Now, the other features. What this is talking about here, I would say that first statement is clearly almost redundant. Most magma remains underground. Well, guess what? All magma remains underground because once it reaches the surface, it becomes lava. Okay, right? But what they're saying is, even counting lava, most of it remains underground. Not all of it erupts and goes to the surface. Okay? Breaks the surface. Underground, it cools and solidifies to form these intrusive rocks as opposed to extrusive rocks like basalts that form on top of the ground. And here are several of the features that deal with that. The first of these is called a batholith. Now, basically, to get the idea here, this down here is all magma, or came from magma, so it would be igneous rock. On top here, for much of the surface, you have sedimentary rock that has been deposited here years and years and years, okay? But the batholith is where the magma has come up, and actually, if it didn't reach the surface, it came so close to the surface that it caused some of that folding, possibly some faulting, but mostly folding, and the pressure from below, and then the upper levels, the sedimentary rock that was up there is eroded away. And that left this hogback, okay, is this area here, possibly the layers, the exposed layers of the sedimentary rock. I can't tell exactly what they're pointing at, but we'll get to that in a minute. But that's called the batholith. Large amounts of crystallized magma, whether it broke the surface or not, generally it didn't, but it pushed its way up and got near the surface. You can also have a stock, which is a smaller protrusion of magma that broke through some of the weaker areas of the sedimentary rock. A lot like a batholith, but smaller. Okay? The batholith intrusions can cause the hogbacks, which basically is bending up the sedimentary layers, and then as they erode away, you get the various layers here of different materials. That's called the hogback. Okay? So batholith, stocks, hogback. Other processes would be things like the dikes. And the dikes are the near vertical places where the magma goes up not in mass like it does in a batholith or a smaller mass like a stock, but just finds a crease or a crevice and goes a weakness and goes up. And these are called dikes. And just imagine you're along here digging in this sedimentary rock, and suddenly it's a really hard black rock. And it was very thin and stuff like this. Those were your dikes, the vertical parts of the dikes. And some of those may have actually made their way to the surface, and now you have a ridge of igneous rock right in the middle of sedimentary rock. And you think, how did that get here? Now, those are the vertical extrusions, but very thin, just they're sort of taking advantage of weaknesses in the sedimentary rock. The sills are when you find weakness on between the layers, and the magma then fills up horizontally, and that then is a sill. The dikes are the vertical, the sills are the horizontal. Okay? Now, just imagine you're digging around down here or something, you go through different layers of sediment, and then suddenly you hit a really hard rock. Where did that come from? Yeah.
Washington, D.C.
Yeah.
I got a friend that he digs tunnels.
Uh-huh.
Just came back from Oklahoma or something like that. They tunnel down and then they horizontal
Right.
fracking.
Right.
But he said years years ago they were in Washington about to do a talk for something. They hit something like that. He
Right.
said, I don't know what that was. We could not get through.
Uh-huh.
He said it looked like it went forever. We just gave up on it. Oh,
Right.
covered it back up and moved to
Right.
another location.
Huh.
He couldn't explain it.
Wow, it could be something just like that. Because I bet you DC is pretty sedimentary because it was really a swamp.
Yeah.
Drained the swamp. Okay. But now how much of this one's true, I don't know, because it was in a novel. I don't know if any of you read the Jack Reacher series. Just Lee Childs is author. I believe that's the one that was in. It was talking about a sort of a doomsday place they had planned somewhere out in the middle of nowhere in the Midwest. They had planned an area that they would evacuate the most important people if there was a nuclear disaster. So again,
Denver, Colorado.
it was probably near Denver. They never said the location, so it may have been more fiction than truth, but I bet you there's some basis in it. And they had done this big excavation, like you say, going down and then digging out. And they ran into something they couldn't get around. It didn't say what it was, but they finally realized they had to give up, and then they never needed it, so they gave up on the whole project. Evidently, the bad guys started storing stuff there. They found out about it. That was what the story was. But I think there is some of that that's going on. People planning these kinds of things. I think there are, what do they call them, survivalists that probably have all sorts of plans like that. And it's just sort of funny. Mother Nature said, "Nope, not gonna do it. Not gonna get through here." Okay. So those are the dikes, the vertical, the sills, or the horizontal. And then the latholiths is kind of another. It's started looking like a dike going up and allowed the magma to go up, but then found a really big weakness near the surface. So now it started pushing the surface up. Remember, like our domed mountains, okay? Sort of like that. And that extrusion of rock in here, lava magma in here, but never broke the surface. And I wonder if on a Stone Mountain is granite, it wouldn't be this. It would be so it probably wouldn't be, but I wonder if it's some process somewhat similar to this. This makes it look dark, but you see, igneous rock can be light too. It can be your silica and stuff. It doesn't have to have the high iron content. And perhaps that's how Stone Mountain came about. Just a huge extrusion there, and that's a latholith, okay? Much bigger than a sill, because it's not as deep. The sills are deeper. This would be near the surface, so it was able to push not as much pressure on top and push this way on up. So those are the other features of igneous rock. Okay, what's the overall picture here? Okay, mountain ranges are composites of many different processes, each uniquely structured. So you will find in one mountain range, more than likely, some folded mountains, probably some faulted mountains, and possibly, not around here, but volcanic mountains. So go out west there and look around, and you may see all three of these within a fairly close area. So don't just say, "Oh, that must be folded." No. Move your hand a little bit, you'll probably find the others as well. Especially apparent along the converging plate boundaries. Okay? Remember the three types of converging plates? Ocean, ocean, ocean continental, and continental continental. Okay? Continental continental, that would be like the Himalayas. Definitely converging plates. I'm guessing most of those are fault. They just look like they are. But they have volcanic activity there too, because anytime you have that kind of motion going on, there's probably going to be some weak areas that volcanic comes through. But because the volcanoes are pushing their way up, or the magma is pushing its way up, it's heating it up, and I bet you get folding as well. So yeah, all of those could be going on. Now, not sure why they put this in here, but probably. This is that little bitty plate, the Juan de Fuca plate. Starts in Northern California, off Northern California here, and goes up along the coast of Oregon, Washington, and British Columbia. This is Vancouver Island. This is British Columbia. This is Vancouver Island, part of it. Here's Victoria. One of these areas right here, probably that one, I think, maybe Victoria, which is a big city there. No, I'm sorry. Vancouver is here. Victoria is on Vancouver Island. That's what I was getting across that. Vancouver, the city, is here. And Vancouver Island is here. And Victoria is the big city on Vancouver Island. Okay. Well, and like I said, Mount Garibaldi is a volcanic, composite volcano in southern Canada and British Columbia. Mount Baker in northern Washington. Glacier Peak here, Mount Rainier here, that's one you see right off of Seattle. Beautiful mountain when it's not raining, and you can see it. Mount Adams is here. Mount St. Helens just over into Oregon. Mount Hood in Oregon. The Three Sisters here. What is that? Let's see if I can see it on mine. Oh, Mount St. Helens. What we've been talking. No, that's I got that one. It's the one below it. Mount Jefferson. Okay, that's it. Mount Jefferson, the Three Sisters. Here's Crater Lake. Now, I don't know if Crater Lake, like I was saying, if that's a cinder cone or maybe a composite. I'm guessing composite because most of the rest of these are. But that's a beautiful area there. Mount Shasta in Northern California. Lassen Peak. I don't know what monocraters are, but they're the bigger ones are here. This is the Cascade Range, they call it. And it happens because of the converging plates between the Juan de Fuca plate and the North American plate. The Pacific plate actually almost seems like it's heading the other way. And then below here you get the San Andreas Fault. I don't know if it starts here because of this or whatever. This is the Pacific plate and the California plate. But that's usually more of this, the transform boundary, rather than the converging boundary. Here are, I found this interesting, plateau basalts. I think we saw some picture of them there, but basically all this area is basalts, which leads me to think this may have one time been ocean floor. And the plates moving around have pushed it up and formed these, because you wouldn't expect to have basalts this far inland. So all these may be pretty recent, and this is what pushed up there. So guess what this is right here? Anyone want to hazard a guess? Great Salt Lake. Why is it a Great Salt Lake? It used to be under the Pacific, and this body of salt water is still there. Maybe the ground is naturally salt. I don't know. It makes you wonder if these are all connected in that way. Okay. They also have a blurb here on a guy with a hearing aid, okay, James Hutton, Scottish natural philosopher who pioneered the uniformitarian geology, son of Edinburgh merchant. You can read that. Quite an interesting character. However, remember, this can't be your source for, or you've already done your papers. All four of you have. That's great. All right, I think that ends the chapter. There is a summary, and again, I say it every time, nothing replaces reading the text. But once you've read the text, the summary does hit some of the high points, and this is one of the shortest summaries I can recall in any of the chapters we've done. The list of key terms is one of the shorter lists of key terms. List them alphabetically, but of course it has the page numbers where they're first either defined, introduced, or described, or explained. And then applying the concepts, even though the other things were short, there's 50 of these questions, which are average or above average. And they have the answers. And then questions for thought, about normal, 17 or so. And for further analysis, about normal, 4 or so. There is an invitation to inquiry, and they say earthquake patterns, and they have a place you can go and read about these and answer some questions if you're interested. And then there's some of those parallel exercises, which are kind of like the examples they have in the text. There's 15 Group A and 15 Group B. For those of you who have the books, the answers for the Group A are in the back. Group B are not. All right, and that pretty much winds up the class for this time. Let's move on to lab. We're going to be right in here for lab. We're not going anywhere. All right, I'm going to set up the lab. I'm going to pass out the labs first, set it up, and then we will, I'll explain it. So for right now, I'll turn this off while I pass out the labs. It to do. Okay, that's what I wanted it to do. Okay. All right, today's lab is latitude and longitude. Okay? Well worth a read, that first page, page 339. But at the very bottom of the page, you'll see it starts talking about materials. We don't have wads of clay that we're going to mess with. But I do want you to read about those as if you had them. Imagine having them. And putting a protractor, you all know what that is, that semicircle, okay, that has angles on it. And look at it, figure out, follow what they're talking about. And they have, well, let's see. For some reason, they didn't print front and back on some of these. Oh, I think she messed up the printing here. There's page 339 and 340. And then my copy has another page 340. So you don't have to read that twice unless you just want to. Okay? Then that 340 doesn't have a back page, but then there's a 341 showing how you can imagine putting a protractor over it. And then laying the protractor the other way. The first way, the top way was latitude, the bottom way was longitude. We're not doing that, okay? But you can think through it, read through it, imagine it, okay? But what you can do, based on your reading of what you just, the first 3 pages, what information does the latitude of a location tell you? Especially if you go back and read that portion on page 339 and on 340 and 341. That's going to pretty much answer that question. Longitude then would be probably the first page plus the rest of page 341, okay, and the top of 342. And now it says number 3, according to a map or a globe, what is the approximate latitude and longitude of the place where you live? Okay? I'm going to get you what you need for that. Okay? Okay, I'm guessing that all of you live in the Birmingham-Bessemer area somewhere, right? Okay? You'll find that everything you need on this pages 30 and 31, you can probably find where you live. Now, I have had a few students who lived a little bit further out and had to turn back a page or forward a page or maybe several pages if they're up or down from here. So that's where you're going to find the answer for number 3. Okay? Now, let me tell you how to use this. And this is what I went to when we were getting back on the first labs, the latitude. The latitude is measured on the horizontal bars here, and this is measured to the nearest to the nearest I can't read this, it's so small. From 22.5 seconds to 45 seconds, that's 22.5 seconds. So these lines are about 22.5 seconds apart, so they're pretty close, okay? You can get a pretty accurate reading, precise reading off of this. So that's where you answer your number 3. Okay? Now, so y'all can work together individually. I don't care. Okay? I didn't care. Number 4. Whoops. And here there's page 342s. I don't know what happened here. She must have had trouble in the copying machine that day. Number 4, explain how many minutes and seconds are used to identify a location more precisely. I mean, how minutes and seconds are used. Basically, go back and read page 339, 340. You got 2 340s, so we'll only read one of them. And page 341. Somewhere in there, and probably what your text tells you, you can pick up that answer as well. Okay? And then, was the purpose of the lab accomplished? You might say, we didn't do very much, did we? Here's the rest of the lab. Okay? That's 5 questions. You got to come up with 20 more points worth of information. Okay? What I have here are 8 cups. This cup has little strips of paper in it. And every strip of paper, this is the Africa cup, every strip of paper has the name of a city in Africa. Okay? So once you've drawn out a piece of paper, write it down. Okay? Here's the Alabama cup. None will be on those pages, but there will be some from cities on other pages in that book. Then you have the Asia Cup. Okay? Then you have the Australian Cup. Not too many in that one. The Canada Cup. Not too many there either. The Europe Cup. The South America Cup. And the United States Cup. Okay? So there's your 8 cups. And what I want you to do, 8 cups, you need 10 more locations. Okay? You'll do a latitude and longitude from each location. Okay, now, let's go to that last one. The U.S. cup. Here is a U.S. atlas. And this is, you might have to do some digging around, but you can find the latitude and longitude lines here. Not to this 45 seconds like you can on that one, but you can find latitude and longitude here. If you have trouble, ask me. I'm here. Okay? I'll help you find those. These are basically about to the nearest degree. A few of them may be half degree. So basically to the nearest degree, not minutes and seconds. Degrees. So this is for the U.S. atlas. U.S. cup. So here's what I want you to do. You get 1 additional city out of Alabama, Australia, Canada, South America, and U.S. Okay? That gives you 5 more cities. You'll get 1 city out of Africa, Asia, and Europe. So that's 3 more. That gives you 8. Then you get to choose Africa, Europe, or Asia. Choose an additional city out of 2 of those 3 cups. That gives you 10. One each from each of these cups, and then one additional one from either two of the three of Africa, Europe, or Asia. Asia or Europe. So you'll get a total of 10 cities. Two of these cups, you'll have 2 cities each. That will be either Africa, Asia, or Europe. 2 of those, you'll get 2 cities. And all the rest of them, you get 1 city. What I would suggest is write it down on the left-hand margin of the page. And since you got plenty of blank pages here, I'd say either on the back of this one or the back of the previous one. I don't care. But list those 10 cities, and then you're going to look up their latitude and longitude. Now, while y'all are getting started doing that, I'm going down to the library and get 3. Usually they have 3 world atlases there, and that's what you'll use for Africa, Asia, Australia, Canada, Europe, and South America. You'll use that for Alabama, and this for the U.S. You can work together, you can work separately. You got plenty to work on. I'm going to pause my recording here while I go down and get. Okay. What constitutes a correct latitude and longitude? I'm just going to randomly choose an atlas here. Randomly choose a page. Okay. This is West Central Africa. Okay. And I'm going to choose a city in West Central Africa that I'm pretty sure was not included in the lab, okay? Because some of these I've never heard of before, okay? All right. All right. The city I'm choosing is Kananga. Okay. It's Kananga. And this, when this atlas was printed, this was called Zaire. This is now part of the country called Congo. It's probably called Democratic Republic of Congo, because there are a couple of other Congos. So this is Democratic. Well, I'm just going to put Kananga, Congo. Okay? Our church actually does some work there, I think. Okay? I just happened to see it. Now, to do its latitude and longitude, I just happened to pick it open to Zaire, which is now Democratic Republic of Congo. That's just south of the equator, okay? And it looks to me to be about 6 degrees south. 6 degrees south. And looks to me about 22 degrees east. Okay? Now that's about as close as I can come on a big map like this. So notice there's the city you drew. You didn't draw it, I did. Okay? Then the latitude, notice there's 2 parts to the latitude. What are they? The number of degrees, and some of those minutes and seconds even. But then you have to follow that with a direction. Latitude is always either north or south. Longitude, on the other hand, is a measure, degrees, may have minutes and seconds, or seconds. And then it's followed by another letter, and the longitude is always east or west. How can you tell? Okay? When you look at the latitude numbers, this one that I found 0. That means that's actually the equator. And above the equator, it goes up to 4 degrees. Below the equator, it goes down to 4, then to 8, and then keeps on going. So if the numbers are increasing as you go up, you're in the northern hemisphere. So whatever number you read on the side of the page, that's going to be north. If the numbers are increasing as you go down, that means you're in the southern hemisphere, so that would be S, and that's where Kananga is in the southern hemisphere, 6 degrees south of the equator. Now, how do you tell whether you're east or west? Again, you look at the longitude angles at the top or bottom of the page, and this one has, reading from the left here, I don't see any there. Oh, here we go. 8 degrees, 12 degrees, 16 degrees, 20 degrees, 24, 26, 28 and 32 degrees. So they're increasing as I go to the right. That means we must be east of the prime meridian. Prime meridian is over here somewhere because that was 8 degrees here, so somewhere over there was the prime meridian, 4, 6, 4, 8, 12, and so on. So we must be east of the prime meridian. If I was in the western hemisphere, say somewhere in the U.S., then the numbers at the bottom of the page would be increasing going right to left. That would then read something like 32, 34, 36, 38, 40. So that means we'll be in the west. So be sure you include the number. It may only be degrees. It may be degrees in minutes. It may be degrees, minutes, and seconds. But put as much as you can, but always follow it by a letter. North or south for latitude, east or west for longitude. Does that make sense? Do I need to leave that up or already shut it down? Leave it up. Okay. Is that what you said? Okay. Won't hurt anything. Okay. And I'm sorry the labs have so many extra pages, and I don't know what happened when she was running these off. She actually ran them off a while back, and maybe that's why I've got so many. She found out she didn't do them right and redid them. I don't know, but I have a whole passel of them. I thought, where did all these come from? Any questions? What?
You said,
Where do you live?
right.
Okay, where do you live? That's
Right.
okay. You did one page off. Okay. Over here, you'll read the degrees, minutes, and seconds of latitude, and you can use this closest line here. That'd be a good one. You've heard that before, haven't you? Okay. And then the longitude, and that would be, now you have to put a letter with it. What letter will that be? It won't list it there. It'll be north or south of the equator. Huh? Yes, of course, we're north of the equator. Okay, and then for the longitude lines, angles, we read those this way. Okay? It looks like to me best for, you can pick either this one or that one, whichever one you're closer to. And you see what they do, they alternate. This one's down here, the next one's up here. I don't know why they do that. Yes, you're going to use that one. That's 3:54 minutes, 0 seconds. Is that going to be east or west? West, because the numbers are getting greater as you come this way. So you go further west of the prime meridian. What did you say? 33. North. Okay. Right. West. Everybody understood? Now, if it's helpful to you, I also bring out the globe. I wouldn't count on the globe to get your measurements. The atlases are better, but this way anyway, if you find the country, say in South America, maybe something in Paraguay, you see it's south of the equator, so that's got to be south, and it's west of the prime meridian, which goes through London, England, or Greenwich, England. So that may help you figure out myself. Okay? Can I go on and pause the recording again? If you have any other questions, remind